This is a short video that will explain the difference between constitutional isomers and geometric isomers. So you will need to know the definition for constitutional isomers, which are also called structural isomers. So those terms you could use interchangeably, but the NZQA exam will only use the term constitutional isomer. So your definition is structural isomers have the same molecular formula but a different structural arrangement. So we've got some examples here. Each of these three molecules have the molecular formula C5H12. So what you'll find in this molecule is 5 carbons and 12 hydrogen atoms, likewise with these other two isomers. The difference is they differ in their structural arrangement. So the first isomer pentane is just one continuous carbon chain, or 5 carbons bonded in that continuous chain. The second isomer we have here, you've got 4 carbons in the continuous chain, and the 5th carbon is what we would call a branch. Now remember, you can't have a branch on your terminal carbons, that is the first carbon or the end carbon here. Branches can only occur on these middle carbons, if you like. If you did decide to put your branch on the terminal carbon, it would in fact continue the longest chain, and you'd end up with 5 in the continuous chain, albeit not a straight line on your page, but it would be a straight line around the corner. So straight is probably not the right word to use. What we've got here in the third isomer is 3 carbons in the longest continuous chain, and on the middle carbon it's got 2 branches, 2 methyl branches. So you've got your CH3 group here and your CH3 group down here. Now you could look at it at a different angle and say that you've got 3 in the longest continuous chain, and then you've got your 2 methyl groups, but still they're going to be on that carbon too. So that's why this one is called 2,2-dimethylpropane. Okay, so that's a constitutional isomer. Same molecular formula, but different structural arrangements. Now when you look at geometric isomers, what happens with these ones is they have the same molecular formula. So these molecules here are representing 2 carbons, 2 hydrogens and 2 bromines, and likewise this isomer, 2 carbons, 2 hydrogens, 2 bromines. They've also got the same structure, because you'll see that it's got a bromine carbon here on carbon 1 and a bromine on carbon 2, and likewise the other isomer down here, it's got a bromine on carbon 1 and a bromine on carbon 2. So it is actually the same structural arrangement. The difference is, though, they've got a different spatial arrangement. So in one isomer, the bromines are both on the same side, so this would be the cis isomer, and in the other isomer, you've got the bromines on opposite sides, so this would be the trans isomer. So what distinguishes these is they have a different spatial arrangement, and that is due to the carbon-carbon double bond restricting free rotation. Because it's unable to spin on that bond axis, that makes it impossible for the bromines to be on the same side when it's got this double bond arrangement. Now there is another definition that you'll need for geometric isomers. You will also need to know what are the requirements in order to have geometric isomerism, because not all alkenes will be geometric isomers. So the first requirement is you do need a double bond, and the reason is it restricts the free rotation about the carbon-carbon bond axis. But you also need a second requirement. Each carbon that makes up the double bond must have 2 different atoms, or they can be groups of atoms. So let's look at the left carbon here. I've circled its attachments in pink. You'll see it's got a hydrogen atom and what you might call a methyl group, although in fact it's not a group at all because it's on a terminal carbon, so this is butene. If we look at the right-hand carbon and look at its groups, which I've got in this teal colour, it also has a hydrogen atom and, for better words, a methyl group. So it does have the two different atoms groups on each of the carbons. So those two teal ones need to be different, and these two pink ones need to be different. But these, the pink and the green, do not need to be the same as each other. It gets a bit confusing, right? Just keep it simple. Look at one carbon, does it have two different groups attached? Yep. Look at the other carbon, does it have two different groups attached? If that's yes, then you will be able to form geometric isomerism. So I hope that clears up the difference between constitutional isomers and geometric isomers.